Hello, my name is Catherine Maclean, and I chose to do problem 10.8 for the instructional video. Alright, let's start by reading the problem, and I listed out all of our variables here just in case. You have been assigned to design a heat exchanger to cool a gaseous process stream. The process stream enters at 20 kilograms per second, and it enters at 431 Kelvin. It has a heat capacity of 3.45 joules over grams times Celsius. It needs to be cooled to 402 Kelvin. Cooling water is available at 85 degrees Fahrenheit and has a specified max temperature of 120 degrees Fahrenheit. The overall heat transfer coefficient is approximately 570 watts per meter squared Kelvin. How much area, which is what we're finding, must the heat exchanger have? So first off, I've already sketched the basic diagram for a heat exchanger. It's a countercurrent heat exchanger, which means our product is going in this way. This is our hot stream in, and this is our hot stream out. Our hot stream goes in at 431 Kelvin, which is also equal to 157.85 degrees Celsius. This will be helpful later on. And it exits at 402 Kelvin, which is equal to 128.85 degrees Celsius. So, hot stream going through. This is our gaseous product. This line in the center of the drawing here basically represents the area where the gaseous product and the cooling water transfer heat to each other. So our cooling water, which is this section here, it enters in here. This is our cold stream. It enters at 85 degrees Fahrenheit, which is equal to 302.59 degrees Kelvin. Again, the conversions are helpful later on. And this is where our cold stream exits. The cold stream exits at a max temperature of 120 degrees Fahrenheit, as the problem stated. That's equal to 322.04 degrees Kelvin. Our heat transfer coefficient, U sub naught, is equal to 570 watts per meter squared Kelvin. Watts, as I wrote here, is equal to joules per second. So I'm going to write that out right now because it is very helpful to have that later on. So it's joules per meter squared times second times Kelvin, which is a lot. Okay. Now that we have all of this sorted out, we're going to start with our main equation, which is area is equal to Q duty, which is essentially the amount of heat that the cooling water takes out of the gaseous product. That is divided by U sub naught, which is our heat transfer coefficient. I wrote all of these up here if you want to look. And our U sub naught is multiplied by our log mean temperature difference. To start figuring all of this out, we know our U sub naught, but we need to calculate our Q duty and our delta T log mean. So to calculate our Q duty, we are going to use an equation that represents the hot stream. So we put out a negative here because it's representing the heat that is leaving this gaseous product as it goes through. And eventually that negative will cancel out, as I'll show later on. So our negative Q duty, our heat duty, for this exchanger is equal to the mass flow rate, which is right here, 20 kilograms per second. Let me write that up here, I forgot. 20 kilograms per second. Quick note, we're gonna have to turn this into grams per second. So that's 20,000 grams per second. So we have our mass flow rate times our specific heat capacity, which is specified also up here. That is, where should I write that? Let's write that here. Our specific heat capacity is 3.45 joules per gram degrees Celsius. Grams are very helpful. They'll cancel out eventually. So we put that there, and then it's our temperature exiting the stream times our temperature going into the stream. Side note, our mass flow rate stays the same all the time, so our conditions are at steady state. Alright, once we have this equation, we can plug everything in. We've already done our little unit conversions that we needed up here. This means our mass flow rate, 20,000 grams per second, times our specific heat capacity for our gaseous product, which is 3.45 joules per grams degrees Celsius. This is multiplied by 128.85 degrees Celsius, as we see right here. That's our stream exiting, minus 157.85 degrees Celsius. Once you calculate all that out, we get a negative heat duty. Our negative number, these negative numbers cancel out. Therefore, our Q duty is equal to 2,000,001,000 joules per second. You see our grams cancel, and then our degrees Celsius cancel here, which is quite nice. Okay, so we have our Q duty. Good. Next, we get to calculate our log mean temperature difference. Now, our delta T1 is equal to our hot stream out minus our cold stream in, and our delta T2 is equal to our hot stream in minus our cold stream out. You'll see it's basically this side is this delta T1, and then this side of our process flow diagram is delta T2. Our equation for our log mean temperature difference, delta T log mean is equal to delta T1 minus delta T2 over the natural log of, again, delta T1 over delta T2. This equals 99.31 Kelvin. This is where it's helpful to use Kelvin. It's a little bizarre because we use Celsius here, Kelvin here, but it works out. And it's the easiest, I think. Then we have 108.96 Kelvin over the natural log 99.31 K over 108.96 Kelvin. Once you calculate all that out, it equals 104.9, or, oh dear, 104.06 Kelvin. Gracious. Finally, ending everything out with our final equation, area equals 2,000,001,000 joules per second divided by our heat transfer coefficient, which is 570. Watch your units. This is very helpful here. Joules per meter squared times second times Kelvin. That is multiplied with our log mean temperature difference, which is 104.06 degrees Kelvin. Calculate all of that out. It equals 33.72 meters squared. Final quick check. Make sure all of your units disappear that you want to disappear. Joules cancel out, seconds cancel out, Kelvin cancels out, and you're left with meters squared. Yay, thank you for watching.